All right, didn't get any questions by email, so I'm just kind of here. I've got the chat window open. I'm assuming Dia is here today, so we'll talk. I'll talk to Dia, but um, again, really don't have that much to do today. So if you got questions, feel free to reach out. All the exams are graded now, so you should be able to see what your grade is on the website. Cool, no concurrent viewers. All right. So for those of you unfamiliar, again, these are office hours. I got nothing to do, so I'm gonna practice the banjo for a little while. Get a little out of tune. practice. That's the second string that's out of tune. Hey, actually, I have a question. Here the discussion, one of my discussion answers, I'm trying to figure out where I went wrong. So let's take a look at what, I'm guessing it's, hold on just a minute. So which discussion board in particular? Because we've had, like, being December course, like, we're constantly doing discussion boards. Yeah, I gotta wait for the lag to get through. But yeah, just type in which discussion board. Let me see. I'm guessing it's the one about reaction mechanisms. You know, of the ones I've graded, I've only seen one person get one of the rate laws wrong. Okay, so as far as why it's called a liquid, it's called a liquid because it has. So I did come and see this comment that people said, well, okay, so people were distinguishing that gas and liquids are not fluids. They're both fluids because they flow. So we call it a fluid because it flows, and we also call it a fluid because it doesn't really meet the criteria for a gas or a liquid. At the supercritical point, both the gas and the liquid have very similar densities and very similar viscosities, and because of that, they can't really be distinguished. You have a mixture of both, but you can't tell the two phases apart. They actually dissolve into one another. So liquid dissolves into the gas dissolves into liquid. So we just call it a fluid because a fluid is a catch-all phrase for any gas or liquid or any material that flows. So we don't want to call it a gas because it's not really gas. We don't want to call it liquid because it's not really liquid, so we just call it a fluid. But yeah, we call it liquid because we can't distinguish it between a gas and a liquid. And both gases and liquids are fluids, so that's kind of a broad term for any phase which flows. Yeah, and it's you can see why people would make that misconception that they think a liquid is a fluid because all liquids are fluids, but all gases are fluids. We just really think of it that way. Colligative properties discussion. All right. We have 10 grams of HCl dissolved in 70.4 grams of water. Give a solution that has a volume of 750 milliliters at 25 degrees Celsius. Answer the questions about osmotic pressure, change in boiling point, change in melting point, and discuss how the freezing point and melting point can be used to find the polarity. So I need the formula sheet from test one, so give me just a minute. So the two things we're going to need here are molality and molarity. And for both of them, we need to know the moles of HCl. So we have 10 grams of HCl. And we're going to divide it by its molecular weight, so 35.5 grams per mole. And this will give us 0.273973 moles. For the molality, it's moles divided by the kilograms of solvent, so 0.740. For the molarity, it's the moles divided by the volume, which is 0.750 liters. So if I just do that math, so 0.37 mole. The molarity here is 0.365 molar. All right, so to do the first one, the osmotic pressure, I don't know why I'm guessing I got it like right here. Yeah, first one's osmotic pressure. Pressure equals trim. The temperature here, it's 25 degrees C, so it's going to be 298 Kelvin. R, 8.314 kilojoules, or kPa liters mole Kelvin. The Van't Hoff factor, I, come on. For HCl is 1.9. And the molarity here is 0.365 molar. times 298 times 0.314. So you get 1,720 kPa. So that's answer number 1 in terms of kP. For 2 and 3, it's asking for boiling point and freezing point. In both cases, the formula is delta T equals KIM. But for number 2, it's so hard having such a tiny screen. We're looking at water. For the freezing point, we use a KF of 1.86 times 1.9 times 0.370. So for the freezing point, which was actually 3, sorry. The freezing point here was going to be depressed by 1.31 degrees. And then for the boiling point, delta T, the only thing that's going to change here is the K there. Oh, just shoot me an email. Every now and then I make mistakes. Like I may be thinking of the wrong problem when I grade it. So just type on the discussion board, hey, could you take a look at my answers again? And I'll take a look. I have to grade a lot of these. Sometimes mistakes happen. For the freezing point, the 0.520, sorry, not 70. 0.366. Yeah, if you did it in ATM and I didn't catch it was ATM, that may have been why I marked it wrong. Yes, we're trying to stick to the metric system. ATM, it's a more intuitive unit. The two big issues with ATM, 1, they're not metric, and 2, it's not a true unit of pressure. So the issue with ATM is that it is ATM. Pressure is formally defined as force per unit area. And there is no such thing in ATM. So you don't see a force and you don't see unit area. A Pascal is defined as a Newton per meter squared. So the reason why we want to work in kPa is, 1, that it is a true unit of pressure, so we can actually get the force out of it. The second is that it is metric, and because it's metric, it's a lot easier to work with in terms of converting between different units. Because to go between ATMs and other units, if you know the conversion factors are not that bad. So 1 atmosphere is 101.385 kPa, which is 760 millimeters of mercury, or torr, which is 1.013 bar, which is 14.696 psi. So if you know these conversion factors, it's not bad, but like atmosphere, if you want to get to any type of unit of force, you have to convert it to something else. kPa is just there. And the other reason why I want you to work in kPa, this 8.314 liters kPa mole Kelvin, that's also the value for R for joules per mole Kelvin. And it's very similar to the moles, 0.314 kilojoules per mole Kelvin. So this can be used for pressure, this can be used for osmotic pressure. This same value of R, this 8.314, also gives you thermodynamics, THD. So we can do units of energy as here as well, so it makes it a lot easier to work with. But yeah, it happens. As with all my grading, if you catch something, just send me an email and I'll take a look at it. Mistakes happen, like it's a class of 50 people. The only caveat I put on this, particularly with exams, look at it within 2 weeks and let me know if you catch a mistake. I generally don't regrade anything if it's been more than 2 weeks and it's handed back, with the exception of like discussion boards. But generally speaking, I want you to look at an exam. Yeah, so for the discussion boards, the thing is, like, these are used for attendance. They're there to keep you on track of the course, but the rule of the discussion boards is submit anything just to get your attendance in. But you can come back up until the day that you do the final exam. So the last 2 days of the class where you're going to be taking the final exam, you can do up until those 2 days. You can redo any discussion board for full marks. So if you decide you have very bad judgment and you decide to put nothing, you just put for attendance up until the last day, you can do that, and on the last day do every single discussion board. I don't really advocate that method, but the goal here is not to penalize you. This is much more of a way to kind of keep you engaged in the course. So yeah, if you're late with the discussion board, generally speaking, get them in, get something down so I can do the attendance. But if you're late with the discussion board and you just put, hey, it's here for attendance, fine. Like, come back the next week when you actually have time and do it. The more important thing is that you do it. Dipole ionic bonds only count as monatomic or also polyatomic ions. So typically, yes, so it will also count for polyatomic ions as well. So polyatomic ions also fall underneath that ionic umbrella because they are true ions. Looking at your future discussion boards, most of these are pretty doable. I don't see any that are super long, except that one. Okay, so you'll do one electric chem that's kind of long. So we have what keeps a dipole bond from becoming an intramolecular bond. So we have intra and intermolecular. So intra is between molecules, and inter, I think, is within a molecule. Hold on, let me look that up. Sorry, intra is between molecules, and inter is within molecules. So I'm not 100% sure on your question. What keeps a dipole ion bond from becoming an intramolecular bond? I think they are still considered intramolecular bonds. So there's intra for between molecules, and there's inter within a molecule. So we also have intermolecular forces. So we can have, particularly with organic compounds, this shows up a lot. So this compound here with the carboxylic acid, this hydrogen will actually do H bonding with a ketone. So within this molecule, even though it can rotate around these bonds, it will typically stick to this six-membered ring because of intermolecular forces. the intro between molecules. So that's why I had to remember was that when you take organic, there are intermolecular forces. So when we're talking about intramolecular forces, we're not talking about true bonding. So when we're talking about intramolecular forces, we're not talking about making or breaking bonds. We're simply saying an attractive force due to differences in charges. So if you have something like hydroxide, and this will be attracted to a ketone, because the ketone here has got the negative part and the positive part. So there is the ionic dipole here. But this hydroxide can also attack the ketone and give us an alcohol. That looks like that. So when we're considering intermolecular forces, we will ignore anything that makes or breaks bonds. We're just simply looking at charge separation and how that causes the molecules to stick. But when we start talking about charge differences that result in making and breaking bonds, this is where we get the Lewis acid-base theory. That is how big does the difference have to be to actually drive that? There is no good answer for this. Generally, these are reversible reactions, so we're going to kind of gloss over details. So hydrogen bonding is a good example of this. So with hydrogen bonding, we have an exchange of hydrogen atoms to make this work. So we've got a hydronium and some type of hydroxide. And yes, we are technically making and breaking bonds here, but from a big picture standpoint, we ignore that detail that bonds are being made and broken. We're just going to say that because of this, it looks closer to ionic. So when it comes to, I guess the way to answer your question is when it comes to intramolecular forces, we're going to gloss over what happens at the microscopic level. We can explain at the microscopic level why what we're seeing happens at the macroscopic level, but at the macroscopic level, we don't really care about making or breaking bonds. We're just going to say that macroscopically hydrogen bonding or ionic dipole or ionic is going on, but we would have to go to the microscopic level to understand why like hydrogen bonding is not as strong as dipole ionic, but we're going to kind of ignore the fact that there are reactions going on at the macroscopic level. Now, as far as what drives it, like what actually makes it go from just attracted to each other from charge differences to actually reacting, there are two factors that affect this. The first is the activation barrier. And the second is just the thermodynamics. So you may have, and this is what you're kind of alluding to with the kinetic energy, and that's collision theory, which we'll touch on, but we'll really go into transition state theory, which is a much more accurate picture. In order for you to make or break a bond, you start with two stable molecules and you have to inherently destabilize them. So if we want to attack a ketone with a hydroxide, hydroxide is stable by itself. This is acetone, it's stable by itself. And what we have to do is we have to form a bond and break this bond. So we end up with an intermediate. I'll erase these top two terms. And this intermediate is a carbon that's stuck between 0 and 1 bonds with the oxygen and 2 and 1 bond with the oxygen that's there. So this would be considered the transition state. Now, if the transition state has a low energy barrier, it's easy to make this reaction go. But if this transition state has a super high energy barrier, even though it may want to do this, it takes too much energy to do this. So a big, easy example of this is that this reaction here, N2 plus O2 going to 2NO2, this is very favorable. Nitrogen would love to do this. Nitrogen has a triple bond, oxygen has a double bond, so it takes the energy of a lightning strike to make these things happen. So if we have a super high transition state, even though it may be desirable to form this final product, if the transition state's too high at room temperature, we just can't access it. The second is the actual energy change. So in the particular case of this hydroxide and the ketone, this really isn't a very stable molecule. So even though there may be a degree of this reaction happening, the reality is that they would much rather just kind of stay hydroxide and ketone than form this alcohol alkoxide complex. So it's two factors that are drive it. One, is the transition state high enough that the reaction simply can't go at room temperature or whatever temperature you're running at? And two, even if you do have a reaction, are you better off than you were before? And if you're not, odds are they're just going to stay kind of attracted to each other just due to charge differences. Expected answer the form. So N is going to be the order, not the primary answer. So for the discussion board this week, you've got the decomposition of bromoethane, and this is the first step, CH3Br2, or CH2 plus Br minus, and it asks you what's the rate of consuming this. So all rate laws here for what we're doing, because we're going to start with power laws, and all elementary reactions can be written in a power law form. You've got K, which is your pre-exponential, and then the concentration of the reactants, in this case CH3, CH2Br, raised to the reaction coefficient, so raised to the first power. So that's what we expect for, I think, for the second question. We're going to ask you, like, what's the rate of consumption? And because it's a product, it's a reactant, it's going to end up having a negative. I don't think I've been taken off for that, though. But yeah, that should be your answer for what's the mechanism. It's just K minus K, concentration of the CH3, CH2Br, raised to the first power. Yeah, the K is, there are actually physical interpretations of this. This is the probability the molecule exists and will run into whatever it needs to run to. And the pre-exponential is just the probability it will actually react. And as we get further on, K here is described by transition state theory. It's a pre-exponential raised to the EA over RT, where EA is our activation barrier. So this is where we get our temperature dependence. As we start increasing temperature, K gets bigger. So as we increase temperature, we increase the likelihood that the reaction is going to happen. if it's going to happen. And we'll talk about it as well. With the pre-exponential factor, it does a lot of things. But k itself just represents that probability. How would we do the lab experiment right? Which lab in particular? So we debate. So the thing about organic, so we during rest of the semester we used to offer Chem 1 and Chem 2 in the evenings, and the reason being is that we had demand for it. So for a faculty member, we're not required to work past 5 o'clock in the afternoon because we are considered full-time employees. We have to volunteer to work a night course, the reaction rates lab. And I did that when I was teaching part-time. I volunteered to teach a night course. But the thing is that we just don't have the demand for a night organic course. We're just now filling our organic courses. So if we had the demand, in principle, we could offer a night organic course, but we just don't have the demand. And even then, we can't require full-time faculty to teach a night course. They'd have to volunteer, and that's really hard to get them to do. I've taught night courses. They're brutal. The labs go from 6 to 9 p.m. And I lived in North Raleigh, so like to drive from Southern Wake to North Raleigh, that was a long day. Reaction rates. Hold on, I'm bringing it up. Yeah, you can see college was definitely set up for people who don't have jobs. I would think honestly a hybrid would work better in this scenario. It would be the compromise of you would have the lectures online, but you would need to physically do the lab in person. I think we could probably swing that better. But again, we're not even currently filling our current sections. So there's directions in a zip file on the course website on how to do the experiment. A lot of this really is just timing. Yeah. So this is what's called method of initial rates. So what you're going to do is you're going to make up solutions of different concentrations, and you're going to see how long it takes for the reaction to run. So I'm guessing here the question is how to do the analysis. The analysis here is actually really straightforward. So if we take the ratio of any two reactions, so let's call them reaction 1 or 2, the pre-exponential factor is not going to change for either of them, and you've got the concentration of, what is it? two reactants in this. Potassium iodide and peroxide. Oh, wait, peroxide is a catalyst. So I think it's potassium iodide and bisulfite ion. But the thing is, we don't know what their powers are. It should be going at 720p. Let me go plug it directly into the router. All right, that should get the speed up. The current resolution is kind of the compromise with, so the higher the step the resolution, the more the latency issues show up. So the longer the lag between when you write something and when I respond to it. Oh, I did not mean to do that. Okay, so let's say reactant A is the potassium iodide, and reactant B is the bisulfite. So we're going to assume our rate law takes the form rate equals K concentration of A to the A power, B to the B power. And we can take the ratio of any two rates that you measure. And that'll be K, A to the A, B to the B for run 1, A to the A, B to the B for run 2. The K's are going to cancel out, and if we take the natural log of both sides, we'll end up with this expression. And this is also in the notes. So this is the rapid way. Let's see if I can bring it in a little bit closer for you. This formula here, the natural log of the two rates from run 1 and run 2 equals whatever power we're raising these concentrations to times the natural log of the concentration of A between reaction 1 and 2, B to its order natural log of the concentration of B between runs 1 and 2. So if we keep the concentration of the A constant between run 1 and run 2, this ends up canceling out, and we get that whatever the order of B is times the natural log of the ratio of the concentrations of B between the two runs, we can solve algebraically for the order. So this formula is in the notes. It's the method of initial rates. It's honestly not that bad. That set amount of time, and I actually have a meeting shortly. So what I'll do is next live stream, I'll start off talking about this and how to do the data analysis for the method of initial rates. So will that work for you? Temperature fits into it with the K. I had to buy this whiteboard. It's my personal property. I mean, people have come up with solutions to doing this, but like, yeah, thanks. And again, we'll start off with method of initial rates for the lab. And I'll just leave that note up here for me. And we'll start out with that tomorrow. All right, thanks for showing up.